So last time we talked about what can be the different sources of errors. We also introduced the concept of significant digits in representation of a number in a finite way. And we gave the definition how to calculate the significant digits. At the end of the last lecture, we started talking about the quantifying the errors in numerical computation, right? So let us rediscuss it today again, and then let's go ahead. And when we are talking about this, in the back of our mind, we do not have any specific source of error in numerical computation, but it works for all the errors. I mean, the way you quantify works for all the errors, but at certain points we will take examples which will obviously be of specific types of errors. Okay, so let's say that we are trying to represent a number. So we have a number, and remember that the number is absolute. So the number I call x. So that's an absolute number. It's known up to infinite precision. There are infinite number of significant digits in it. The exact value of this number, so x is the symbol for the number. The exact value for this number we wrote as x star, and the approximate representation of this number the Jamboard is already shared in your class, Google Classroom portal, so you can get it from there. The approximate representation I call x. This. So that is, you can call an estimate of the number or approximate representation of the number. All right. So these are just definitions. So the number I call by the letter x. So that's a symbol. So everything with the number will have this letter x. The exact value is x star, and the approximate value is x with this bracket. Now error. So what will be the error in this in representing this number? Well, so if I write it as delta x, let me write this as delta x. So this is x minus x star. Or if we choose to write it as x star minus x as well, it does not matter. So this has a sign depending on whether x is greater or x star is greater. It does not matter you write x minus x star or x star minus x once you do that consistently for all the numbers. Okay, so it's your convention what you write, but you see that it depends on a convention. And because of that, we introduced the concept of absolute error, which is of course modulus of x minus x star. So now it doesn't depend on which one is greater. Okay, and again, when you are doing the computation, you may not know what the exact number was. So you may not know what is x star. You only have an approximate representation, which is this. So you cannot have an absolute error known to you. What you can have later, rather, is an estimate of the absolute error. So when I call estimate, so I write with this sign. So this is the estimate of the absolute error. So it better be greater than the actual error, actual absolute error, because if it is lesser than the actual absolute error, you are underestimating the error, which is never good. So this quantity should be greater than or equals to x star, delta x star. And we said that we can represent the number. In this case, we can represent x, or you can write x as x star, which is the actual number, actual value of the number, plus minus delta x. Okay, so let me not write it in terms of delta x star. So it's better to write this way because we have already come to the estimates. So in terms of the estimates, x star should lie between your estimate of x plus estimate of delta x and estimate of x minus estimate of delta x. Okay, so this expression is also, you will see similar type of expression when you are talking about measurements. So you write it in the measured value in terms of the measured value plus minus delta x. So that's essentially what it is written here. And we can come with a concrete example. The concrete example is the following. So let's say example. So x star is 1.234, x is 1.23, and delta x is, in our definition, is minus 0.004. Delta x star is plus 0.004. I'm not writing it again. And what is the value of, so what is this range? So if I say that my delta x estimate is greater than delta x star, so this is 0.005, then I can write that x star, which is 1.234, lies in between x plus this, which is 1.235, and x minus that, which is, what is that? 1.225, right? Now this is a correct statement. Yeah, this is a correct statement to say, and then there is, I mean, maybe I am exaggerating the error, but this statement is correct. So that is, I should be happy with. Okay. So this is what we discussed at the end of the last class, and I wanted to start it from here. So any question on this or any doubt, please ask, otherwise we'll proceed. All right. So let me proceed. Now, so when we discuss absolute error, the absolute error in a number can be very large or very small. But what really matters most of the time is how much that error does compare with the number that you are measuring. So that's not an absolute error, that's the error relative to the number that you are measuring. So that's called a relative error. And at the end of this lecture, it will be probably clear to you why we are discussing all these when we will put it into context. Okay. So what should be the definition of relative error? So it's very simple. So I write it in terms of delta star. Delta star is delta x star, absolute error in x, divided by mod x star. And you see that there is a problem if x star is 0. So this is only defined. This is only defined when x star is not 0. You don't define relative error if x star is 0. Okay. And let's go back once here. You see that in the first lecture itself, we said that before putting numbers into computers, we will make sure that those numbers are dimensionless, right? But if you forget that for the time being a little bit, and you say that this x has still a dimension, then you see x star has the same dimension. The approximate representation of x as the same dimension, the error, the absolute error, and the estimate of the absolute error, everything has the same dimension as x. In that context, delta star is always dimensionless. Okay. Nevertheless, as I said and try to emphasize again, that when you put a number into computer, you must make sure that it's dimensionless. Okay. So this, if I have, then I can write. So then I can write my x star as x okay. So remember that previously this I can write. So if I am writing in terms of delta x star, so then I can just write this we did last time, that x equals to x star plus minus delta x star. So equivalent expression I have written here. Now again, estimate of the relative error, just for this as the same reason before. If I call this delta estimate, this should be greater than or equals to delta star. This should be understandable right now to you, because that's what that we have, that logic we have gone through once. Okay, so these are two different types of ways we represent an error in a numerical computation, and now we will try to put these into context and see that what these amounts to. So if I give an example, maybe let's take the same example that we took last time in the last page, that I have x star as 1.234 and delta x star as 0.004. So this, with the same example, my delta star will be 0.004 by 1.234. And I'll leave you to calculate this, what this number will be. But that's the relative error. Sorry, that's the relative error in a number. Okay, so any questions so far again? Else we'll proceed. All right. So before going any further, let us ask the question that in general, when we are trying to write a number, let's say we are trying to write a number. Let's say we want to write down a number. Okay, so can anybody tell me that what is the first thing that I have to do if I wish to write down a number? What is the first thing that I need to do? It may, because we are so familiar with numbers, it may seem very simple for us to write down a number, but what is the first thing that one needs to do if one needs to write down a number?
So decide on what base to use.
So first I have to decide on which base I use, right? Usually we use base 10 numbers. So what do I mean by then base 10 numbers? So let's start with an example. So an example. So let's take the same number, 1.234. Okay. So what does this 4 digits and that decimal point means? This means that to get the number, get the actual number that I am talking about, that absolute number. So I have 1 and then I have to multiply this by 10 to the power 0. Add to that 2, multiply that by 10 to the power 1, minus 1. Add to that 3, multiply it by 10 to the power minus 2. And to add to that 4, multiply it by 10 to the minus 4. Right? So that's the number. So if I write x is this, x star, this is my x star. So what am I doing here? So I have a power series in 10. Just a second. So I have a, yeah, go ahead first.
So there would be 4 into 10 to the power minus 3, no?
Yeah. Right. So it's minus 3. So what am I doing is that I have a power series of 10 and then I am multiplying several things with that. So I can write this as D. D is the digit, if you wish. And in this case, D0 into 10 to the 0 plus D1 into 10 to the, or D minus 1 into 10 to the minus 1, etc. Right? So that's how I can represent a number. And this is in a base of 10, as somebody was pointing out, because this is a power series of 10. I can as well have represented a number in power series of any integer. So this 10 could have been 2, it will be binary, or it can be 8, or it can be 16, or it can be anything that you want. It really doesn't matter. So when you try to represent a number, you can use anything. Right? So the first thing that we need to do is to choose that base. So we choose a base. Say B. The base is B. B equals to 10 in the previous case. And then I write down x equals, and let me use a little bit different index, and it will be clear why I am doing this here. So I write D, the mth digit if you wish, b to the power m, and D m minus 1, b to the power m minus 1, and then I will have, say, something like b m minus n plus 1, b to the power m minus n plus 1, plus and if it's an absolute number, remember you have infinite precision, this can go up to infinite time. Right? Now, let's say that instead of looking at this number, I was looking at a different number, and let me erase this out and write a different number here. Say the different number was 0.0123. Okay. So how will I write it now? So I can write it as D0, or in that case it is 0 into 10 to the power 0 plus 0 into 10 to the minus 1 plus 1 into 10 to the minus 2 plus etc. Not writing everything. Okay. But you see, it's a complete waste of writing these two, because anyway you know that these are 0, right? So what matters is the first digits in the from the left, which is non-zero, and this dm is the first digit from the left, which is non-zero. So this, in this way, when I am writing, this is not equals to 0. If it was 0, I would have not have written it. That's it. Okay. And one thing I forgot to mention when I was writing the first number, that this decimal point essentially, or whatever. So it can be a binary point also, or a trinary point if you wish. The base is 3. But whatever it is, it represents where you start to get the negative powers. So the decimal point will be at that dashed line. Right. So this is how I have represented a number. So can anybody, so is this clear that when I have written down this number, I have chosen a base b, and then in that base b I have written down the number x. Okay, or I should write x star, which is the absolute value of the number, and it can have infinite digits. So any question here so far? So then let me ask you. So in this representation, what is the leftmost significant digit? Shudhanshu.
Is it 0?
Yes, sir.
So what is the leftmost significant digit in this representation?
D0? No, it will be 0 in this 0.0123, right? So it will be 0.
No, I am talking about here.
So DM.
That is DM. So what is the leftmost significant digit here? It's not 0. It's 1. You should go through the definition of the significant digit. Okay. The one which is non-zero from the left, the first one which is non-zero from the left is the most significant digit, and that's what is DM. So DM is the leftmost significant digit. So this is my leftmost. Okay. So let's say that I have n significant digits in this. So what is the rightmost significant digit? If I have n significant digits in this?
D m minus n plus 1.
So this will be the rightmost significant digit. Okay. If I have n significant digits, we will see that shortly. But you can get that from some examples. So I'll not go through the examples right now, but try to see the. Let me write down 2, 3 numbers here. Okay, and so these are 2 numbers. Try to calculate the significant digits for these numbers. So I have to give you the precision at which I am representing the numbers. So that is 1, 2, 3, 4, 5, 6, 7, 8. So 10 to the minus 8. Minus 7 rather. Okay. So what is the rightmost significant digit in these 2 numbers? If I have the precision is 10 to the minus 7.
1.
1 in both cases, right?
Yes, sir.
Okay, so that's fine because that's the place where you have 10 to the minus 7. Fine, that's the 7th place after the decimal point. And these are binary decimal representations only. All right. So there is a theorem which is useful. I'm not writing down the statement of the theorem very explicitly, but it says that if we represent the number as in last, no theorem will say this, as in last board, and it has n significant digits, or it has n significant digits, if its absolute error is less than half of nth digit from left. Not nth digit, so I should say, what should I say? So nth base from left. Okay, so let me write down it explicitly, then it will be clear, because it's, so delta is the absolute error, delta x, this is the estimate of the absolute error, is half. What was the term in the nth position? This is the term in the nth position. If you calculate from the left, so this will turn out to be the term in the nth position. So this is what the base is, which is b to the power m minus n plus 1. So this delta x will be less than half of b to the power m minus n plus 1. b is 10 in this case, so let's write things in terms of decimal. So b equals to 10, so let's write things in terms of decimals. It's easy to understand. We'll do binaries in the next class. So it's 10 to the power m minus n plus 1. Okay, so let's call this m minus n plus 1. Let's call this n. So this is just for our later convenience. Okay, so what is happening here? So what is happening is that you are saying that a number which is represented in a computer or with a finite number of places, finite number of significant digits, that has n significant digit if the absolute error is less than this number. Okay, it has n significant digits if the absolute error is less than this number. So let's try to see if this is true. Let's try with one example and then it will be clear. So this is a theorem, and you really don't need to explicitly prove it. I can just show you an example that will convince you, I guess. So let's see. So let's say that I have, so this is an example. So I have the number 0.01996, say this number. Okay, and I have 3 significant digits. So this is equals to x. If I have 3 significant digits, so what is x star? Somebody, what is x star if I have 3 significant digits? You have to round it off.
0.0199.
No, so point
1.99.
is it? See, if it is 1.99, that's a complete different number, right? First, I have to round it off. So I can have only 3 significant digits. See, the leftmost significant digits, obviously I cannot change. If I change the leftmost significant digit, then I will completely change the number. So that is not possible. So I cannot
1.9
change.
into 10 to the power minus 2.
1 second. So I cannot change 3 numbers here. So I cannot change 199 because 3 significant digits are there. But you see, after the last 9, there is a 6. So I have to round it off. And once, if I try to round it off, the number becomes 0.02. But because it has 3 significant digits, it has 2 more zeros, which are significant. Remember that the zeros up to the precision is significant. So in this case, the precision will be, so precision is so I'm writing of the order of, because we'll see how much it is, 0.00001, little more than that. I mean that digit, the 5th digit after the decimal, so that you have rounded off, right? So x star is this. So how much is delta x here? So delta x, remember x minus x star is our definition. So it was in the first page. X minus x star is our definition for delta x. So how much is that?
Zero point zero four.
Right. So this is the delta x. All right. Now, if I had to write this number, x star, let me write it here. Let me write this number in this representation, in this way, because remember that that is what I have to do. That's what is the first line I have written in the theorem. So how will I write this number? So what should I start with? Somebody.
2 into 10 raised to power minus 2.
2 into 10 to the minus 2, then plus
0
so I'll
into 10
write
raised to power minus 3.
0 10 to the minus 3 plus 0 10 to the minus 4, and that's it, because I have 3 significant digits, right? So what is the value of L? What is the value of M? What is M?
Minus 2. Minus 2.
See, M is minus 2, right? So it's clear, because 2 into 10 to the minus 2, 2 is the first non-zero digit here. So when I write it in this way, this is the first non-zero digit, and then M is the exponent of the base in the next, the power of the base. So the power of the base is minus 2 here. So M is minus 2. All right. And you
So
also
here,
get, yeah.
the n would be minus 4, right?
Let's see. Let's see. So what is delta x? So this I can write. So this number is delta x is 0.0004. So I will write delta x estimate less than half times 10 to the power something, right? So what something will suffice? 10 to the power minus what will suffice? So this is less than
Minus 4.
0.0005, right? So 10 to the minus 4.
Sir, actually there should be one more zero and delta x.
Right.
Sir,
1, 2, 5. 1, 2, 3, 4. Okay. There should be one more zero at delta x. Let's see. Yeah. It's this, right? Yeah. So this is less than, then which is half into 10 to the minus 4, right? Because this is 0.5 already, half is 0.5 already. So this is this. So what is your value of L? L is, so L is this quantity, which is m minus n plus 1, which is sitting over here, which is should be matching with minus 4. So L is minus 4. So if you put these two, where should I put these two? So I can use this expression now. So n is equals to m plus 1 minus L minus 2 plus 1 plus 4 equals 3. So that is the number of significant digits what we had. So this theorem, I did not prove it, but this example shows that the theorem works. Okay, so this is actually very useful. We'll see it shortly when we'll. So this is the theorem. Now we will use this to find out the relative error, and finding out the relative error becomes useful if I use this theorem. Okay, so any question here?
So what is L again?
L is just, for convenience, I have defined this as L. Yeah.
Okay, so the last, like the last digit power, right? Sorry, the error's power, right?
So this is the power of the, so 10 to the power, this is the base of the last digit. So the last digit here, the last digit means the last significant, the rightmost significant digit is this one, right? So this is multiplied by this quantity, which is what I am writing there.
Yes, sir.
Okay. Intuitively, it is clear why it will be half here, because you remember that when you are calculating absolute error, the absolute error is, there is a modulus. So the absolute error can never be greater than 5, and greater than half.
Yes, sir. So I thought it is like for rounding purposes, more than half we take it to the next place, and less than
To
half
the
we...
next. So more than half is not possible in rounding purposes, right?
Yes, sir.
So you immediately see that this is in context of rounding of a digit.
Yes, sir.
So this is in context of round of error now. Okay, so round of error will have this property. Let's see what happens to the absolute error. So if an approximate number has n significant digits, then the relative error delta is less than or equals to 1 by 2 dm. Dm is the digits. What is dm? Dm is the first digit, first significant digit, right? Into b to the power minus n plus 1. Remember that dm is the first significant digit. So by definition, it is non-zero. This is rather easy to prove. So I have delta. So so you can call this delta star as well. Delta star is the actual, the definition of absolute error. So this is equals to delta star, delta x star This is just I'm writing the definition from the second board. Now what is this? So this, the denominator, I can just write the expression for the number the way we were writing earlier. And let me write everything in terms of decimals. And it goes on forever because it's an absolute number. The error we have seen that is to be less than whatever you are writing down earlier. So it is to be less than half of 10 to the power m minus n plus 1. So this lesser than equals to. The denominator is lesser than equals to the denominator. The numerator is exact. Now, in the numerator, every digit here only adds up to the number, right? So if I just keep the first digit, if I don't take the other digits, then the denominator will be lesser than the original denominator, right? So if say the denominator was 1.234, that's my favorite number today. And instead of using this, I use just 1 by 1. So this is definitely, this number is definitely larger than 1.234, right? Is that clear? See, if I round it off to the first digit itself, then the total number, the numerator by denominator, is always that rounded off numerator by denominator is always greater than what is written here. It's straightforward, right? So which means I can write this as delta star less than or equals to half 1 by dm 10 to the power m minus n plus 1, and then you so this is not correct. And at this point, it is useful to take a logarithm in both sides. So I can take a log 10 of, we'll see something interesting happens shortly. This is lesser than equals to minus n plus 1. Or you can write alternatively n, which is now the significant digit again, should be lesser than equals to 1 minus log 10 of fine. So this is just combinatorics which led us to this point. Any questions so far here? All right. You see, if I have the base 10, the average error I can make is like 5. Okay. Sorry, the average digit that I can have in the first place is like 5. I mean, you can have 1 to 10, and then I say that 1 to 9, 0 to 9, and I say that DM average kind of, this is kind of when you say rule of thumb type of thing. So this is like 5. Okay. So then what does it tell you is that n is less than equals to 1 minus, so this 2 into average dm, so this is kind of, let me put a tilde over here, so this is a kind of estimate of n, or you can say rough what is the number of digits, number of significant digits. It can be go up by 1, but roughly I want to know. So that is n tilde. So I have 1 here, and minus log 10 of 2 into average of dm is 5. So 2 1 to 5 is 10. So I will get another one which will cancel this. So this is log 10 of delta, minus log 10 of delta. So if delta is like 10 to the minus 4 in our example, so delta 10 to the power 10 to the minus 4, so then n tilde is of the order of delta, of the order of 4. So the number of significant digits is of the order of the exponent of the decimal exponent of the relative error. Okay, so that is useful because so I know that if I have done a relative error which is like 10 to the minus 3, then I have roughly 3 significant digits in my number. Okay, so this is, so remember that when you are doing your lab in the first year, you are always calculating relative errors, right? So that tells you how many significant digits, roughly how many significant digits you have. So you have relative error of 0.01, you have roughly 2 significant digits.
Excuse me, sir.
Yeah, go ahead.
So here you could say that average of dm is 5, but for basis ternary basis where like there are odd number of total possible
Right, so
numbers. Then
I understand. So this is, that's why I said it's a rough estimate. Obviously, it will not be true. It will not be exactly true. So this 4 can be 3 or 5.
so there we have to take like what do we do in that basis?
No, see, you can exactly find out what is n from this expression, right?
Yes, sir.
So you find it out exactly.
Okay, sir.
You put in your dm, you have a number. So the first significant digit is very well known to you, right? You have to know one significant digit. dm, you know. If you have an estimate of delta, you put in delta here and dm here, you get n. This is because we are mostly tuned, our brain is tuned in binary. This helps because then I can say that in binary, okay, so 4th decimal place, so that means that delta is 4th 10 to the minus 4, so I have 4 significant digits. So that's the
Yes,
kind of
sir.
rule of thumb we can use because we use binary representation. It's of not much use in a computer computation.
Sir, in the expression, should that be delta star in
Where?
tilde calculation? In tilde calculation.
Here, yeah. See, that's what this should be delta star. There it doesn't matter in the right hand side. So this you put in delta star or delta doesn't matter because it's all of the order of. It's not the exact thing that you are writing, right?
Yes, sir. Yes, sir.
Okay, so let's do 2 quick things today and then we'll call it a day. So we have talked about so much of relative errors. So now let's start to look at some operations. Okay, so the operation is like, say, what is the most used operation in computer? Summing 2 numbers, right? So summation. Or sum, let's write sum only. So if I want to sum 2 numbers, we'll see in the next class or next to next class that summing 2 numbers are not so straightforward. So if you want to sum 2 numbers, so say I have 2 numbers x1 and x2, and I just want to do this operation in a computer. Okay, how will the error propagate? So what we are discussing here is error propagation. That means that I know the error in x1, which is delta x1. So this is error, this is not absolute error. And this is delta x2, again error in x2. The way we defined it is like x1 minus x1 estimate minus x1 star, and this is x2 estimate minus x2 star. Right, so these are the errors in x1 and x2. The question you are asking is, what is delta x going to be? At this, you know from your lab class that this delta x is delta x1. Again, I'm not writing relative error, sorry, absolute errors. I'm writing just errors. Delta x1 is delta x1. Delta x is delta x1 plus delta x2, right? But you see, this is true, right? Now, what about the absolute errors? What about if I ask the question, what is delta x star in terms of delta x1 star and delta x2 star? So let's try to calculate the absolute error here. So what is the definition of delta x star? This is, first I will write x1 plus x2, estimate of that, minus x1 star plus x2 star. X1 estimate is x1 star plus or minus delta x1, or let's say plus delta x1. Okay, so one thing I forgot to tell is that all these numbers have same sign. It doesn't matter if they're positive or negative, but if one is positive, the other is also positive. Otherwise, it will just become a subtraction. That's why. Okay, x1 and x2 have same sign. So this is x1 there is no estimate here. And the modulus of that, which is modulus of delta x1 plus delta x2. Now see, delta x1 and delta x2, are they need to be positive or negative? Can they be negative, delta x1 and delta x2? They can be negative, right? So the error can go in the either way. So that we have seen one example where the error was minus 0.0004. So because these can be negative, in some cases one can reduce the other error a little bit. But the maximum error cannot ever be the summation of these two. Maximum absolute error can never be the more than the summation of these two. So which means that if I ask what is the absolute error in this, the absolute error in this is always lesser than or equals to the absolute error in x1 and absolute error in x2 summed over together. Is this all right? So I have come to the end of today's discussion now. So we'll start from here. But if there is any question, I can take. We'll rediscuss this part the next class again.